Hi there. Quick video. This is going to be sort of like an update to episode 1 of the Zero Pages, like a 1.2. Somebody got a request, had a request for me to explain this blink test program. Um, if you are not comfortable with 6502 or assembly language, you should continue on to the episodes 2 and 3 of the Zero Pages, because this is going to go real fast, and episodes 2 and 3 and 4 and 5 cover a lot that will be important for you. So yeah, I guess like spoiler alert. But I'm going to go through this real quick. This is not going to be like the other Zero Page episodes where I put together a lot of graphics and visual aids, because this is just literally going to be going through and explaining line by line what it is that the code is doing. Again, if you need more details, I would suggest watching the other episodes of the Zero Pages, which go into a lot more detail about what's going on here. This is just to explain the blink test program, since it seems like some people wanted to know. So the first thing here is the header segment. Each part of your code is divided up into different segments. The segments are defined in a configuration file for the assembler, which I'm not going to go into here. And basically it instructs the assembler of kind of what your code is meant to go into, where it's supposed to live. So this is telling your assembler this is header. Header is literally only useful for emulators. It has nothing to do with an actual NES. If you want more details on the header format, you can find it here on the NESDev wiki, which explains the format of the header. But basically, we are defining 2 by 16 kilobytes, so 32 kilobytes of prog ROM for our program here. 1 times 8K of character ROM, which is totally useless for what we're doing here because we're not going to use it at all. And then we're using mapper 0, and all the rest of the stuff is set to 0 because we don't care about it for this test that we're doing. If you go to, where are the mappers? So there is a list of the different mappers. If you go, you can even see that there's mapper 0, which is the simplest mapper, called NROM. Some games in the homebrew community still use NROM, since this was the first mapper that Nintendo used on the NES. It's the simplest, most straightforward mapper for the games. So yeah, so the header is just designated so that the emulator knows. The assembler adds this to your NES file, and the emulator then knows what kind of cartridge you're creating here. So you're telling the emulator that it's a 32K prog ROM with an 8K character ROM, mapper 0, whatever mirroring and other stuff gets set up here by these values. We don't care about this here in this particular example because we're literally just trying to make something really super easy run. I will again state that if you're not familiar with assembly language, what I'm going to go into moving forward is potentially going to confuse you, and I would then urge you to check out episodes 2, 3, 4, and 5 of the Zero Pages. But foraging along here, this is a startup segment which we don't use, so I'm not going to explain it. This segment is the Zero Page. So the 6502 has an addressing mode where it can read the 2K of RAM in a sort of a shorthand way. The first 256 bytes of that RAM can be addressed using only 8 bits instead of 16, and so that's faster to decode and to access that first 256 bytes of RAM. So that's why I called the series the zero page, because it's shorthand and it's meant to be faster than going through my longer streams, which I haven't posted in a while. But anyway, so this is essentially designating this part of the code a RAM area, where we're defining things that we want to store in the RAM, like variables. So we have a flag variable that we're reserving 1 byte for, and we have a counter variable that we're also reserving 1 byte for. And those are the only variables we're using in this program because, again, it's super duper simple. This next segment here is the code segment. In the configuration, the code segment is defined for the assembler to know that your code is following. It's defined saying that you're writing your code into that now 32K of prog ROM that we have defined. So this is all my code that's getting started here. Before we actually get into the meat of the program, we're defining this as a subroutine. The reason I know it's a subroutine is because it's got this RTS, return from subroutine, instruction at the end of it. This is a little subroutine that I've created to wait for a vertical blank to occur. The vertical blank occurs once 60 times a second, and we can detect that it has occurred by reading from address 2002, which is a register in the PPU, and checking to see if a particular bit is set using this clever bit and BPL sequence. This is something you can read up on, again, the NestDev wiki. Normally I'd go into more detail on it, but because I'm just kind of going through this real quick to explain it line by line, I'm not going to go into too much detail. Just suffice it to say that when this register has one of its bits set, we can actually, we'll look that up right now here, so we can see which bit it is. Then the CPU is, or the PPU is in the period of V blank, where nothing is being drawn on the screen, which means that it's safe to update the PPU for the next frame that's going to be drawn. So yeah, that's what I thought it was, but I couldn't remember off the top of my head. Bit 7 is set to 1 if we're in the V blank. So if you've drawn a full screen and you're at the bottom of the screen and you're waiting till the time that you would draw the next frame, this bit would be 1. If you think of an electron gun on a CRT scanning from the top left to the bottom right, that is the period where after you've reached the bottom right of the screen, nothing is happening because you've traced the whole screen, and now you have to wait the full 1/60th of a second that remains to go to your next, go to drawing the next frame. And that's the time that you have to update what you want the PPU to do for drawing your next frame. You don't want to do it while the PPU is drawing the next frame, because that will change what's on screen, potentially to disastrous effects, sometimes to cool effects. For some of the special effects that happen on the NES are done that way. Anyway, so that's what that's checking for, to make sure that we are in the V blank period, and we need to do that for a specific reason, and I'll get into that in a second here. So this label called reset is what gets called when the 6502 is reset, or when it's powering on. Well, how does it know to do that? How does it know to get to that? Reset isn't anything special. I could have called this, I could have called this PlayStation or Xbox or or Flugelgorg or whatever. It doesn't really matter. The reason it knows to call reset is this segment called vectors here. This segment vectors is essentially another part of the program. It if you look at the way that the 6502 works, at the very end of the program, it expects that there are three different addresses. There is the address of the code that you want called when the non-maskable interrupt occurs for a vertical blank. So you can set the NES up that when you've drawn a full screen at the end of that period, incidentally, that will be at the same time that that bit that we check here is 1. It will also call code at this label using an interrupt, which will interrupt the flow of your code wherever it is to go to this label to run. There is this reset label here, which is where you want the 6502 to go when either it powers on or the reset button is pressed. And then there is this final address, which we've set to 0, which is an interrupt handler. If you have a cartridge that uses an interrupt or creates an interrupt on the CPU for something, for example, the MMC3 cartridge mapper has the ability to, as it's drawing the lines across the screen, it counts how many lines it's drawn from top to bottom, 0 to 239. And you can tell it to create an interrupt at any of those horizontal lines so that you can do some sort of clever effect if you want to, which I won't get into, but basically you can do stuff where you're changing how the PPU is drawing while it's in the middle of drawing to achieve something that wouldn't be otherwise possible. So if you're using a cartridge that has that, you can specify that you want it to call code at a particular address to handle that. In this case, we're just setting it to 0 because we're not doing that. So we don't really have any use for that. So that's what we're doing here in this segment. Going back to our reset code, this reset label is, like I said, nothing. The name is not important. It's the fact that we defined it down here in our vectors section. So when the 6502 powers on, it looks for the address in that location in the vector segment and immediately goes to this reset here. Now, when the 6502 powers on, and again, I go into a lot more detail in later episodes of the Zero Pages, when the 6502 powers on, it's not in a known state because the CPU is just powering on, and the RAM could potentially just have random junk in it from starting up from scratch with nothing in it or no known good state in it. Every NES game essentially does the same thing to kind of initialize the NES's RAM and environment in the same way so that you're in a known good operating state before you actually start your game up. So first you want to disable your interrupts. You don't want anything interrupting your code while you're in the middle of trying to initialize the environment. Like if the PPU starts drawing random stuff on screen and creates and calls the non-maskable interrupt at the end of one of the frames, calling this code, and you're still in the middle of initializing your game, bad things will happen. So you want to disable those straight away. We also disable the decimal mode. That's more of just a sort of protective thing. The 6502 doesn't have a decimal mode, so there's really no specific need per se, but all the example code I've seen kind of recommends doing that. So yeah, we do that too. Then we disable the audio functionality in the 6502 audio processing because we don't want any random sounds or anything happening, because when the 6502 booted up, it happened to have something that might create random strange noises, right? So we want to get that cleared out so there's no sound. So we do that by loading X with the value 40, and then we store X into the location 4017, which again, if you go into the NestDev wiki and you look up what that register is, you will see that it says it's the joystick 2 data, and frame counter control. So what we care about here is the interrupt part of this. And what we want to do is we want to set the interrupt to be off, right? So this is the first 4 bits here, which we've set to 0. And then the second 4 bits here, we have bits 1, 2, 4, and 8. We're setting 4 to 1, which, sort of contrary to what you might think, is actually disabling the interrupt. Because, where does it explain this? It's an interrupt inhibit flag. So you're actually setting the bit to tell it to stop the interrupt rather than setting it to turn the interrupt on, which I know that's kind of confusing, but that's just the way that it works. The next thing we're doing is we're loading X with the value FF, 255 in decimal. And we're doing this because we're going to initialize the stack. The stack grows from the top down, and so we're telling it to grow. The stack lives in a specific area of memory. The base of the address, I believe it is 02 always. Is it 01? It's 01, sorry. Right. So it lives at the end of the RAM. So by setting this stack register, the S register, to FF, you are setting the stack register to actually be to 01FF. And as you push things onto the stack, the value decrements rather than increments. So if you push a register on, it'll go down to FE and then to FD, and then when you pop it off the stack, or you pull it off the stack, because they use push and pull rather than push and pop like in x86, it re-increments back up. So you have to initialize that. There might be reasons why you don't want it to start at FF, but that's sort of the way that most people do it. Again, this is kind of like the general best practices of the way you should be doing your initialization. So then we increment X, so it goes from 255 to 0, just because it's a quick way to then have X equal to 0, and then we want to store that into these 3 registers. So by storing it into these 3 registers, we're disabling the non-maskable interrupt. We're actually doing a few things here, so let's take a look. So we are in the controller, we are setting all of these bits to 0. So we are disabling the non-maskable interrupt. We are setting the PPU master slave select to 0. We're setting the sprite size to 8x8, the background pattern table address to 0, the sprite pattern table. None of this is actually important to what we're doing. I'm just explaining why it works, why we're doing this. But the most important part is we are turning it off. We don't want a non-maskable interrupt to occur while we're initializing because the system isn't ready for our code yet. And we're not ready to start drawing. So then after that, we are also setting 2001 all to 0. So we're saying we're using normal color mode. We are hiding the leftmost pixels, the background in the leftmost 8 pixels. We're hiding sprites in the leftmost 8 pixels. We're turning off the background, we're turning off the sprite, and we're turning off these emphasize bits. Now, these emphasize bits are important for what we're doing later. Basically, what they are is they allow you to kind of change the way that the red, green, and blue values are expressed by the NES hardware itself. You can use them to make sort of different sets of colors than you might otherwise get by emphasizing red or green or blue. It's almost like if you think about how when you're drawing something using RGB, if you apply extra R to everything, everything starts to have a red tinge. It's the same thing. It's just that this is at a hardware level. So we're just setting that to be off right now so that we get all black. We don't want anything on the screen to start off with. And then register 4010 in hex. We are also setting that to all 0, and that is one of the audio registers, and we are, so it's for the digital sample playback, and we are just basically turning that off because we do not want any audio playing at all. So once we do that and we've turned off everything and we've gotten our code into a situation where it's sort of everything is shut down and we know we're not going to get any interrupts or anything is going to mess up our code, we wait for one VBlank period. We wait for the PPU to successfully process one full screen so that we can get started with what we're doing here in our code. Once we've done that, we have a loop here where we're clearing out all of our memory. And so what we're doing is we are loading A with 0, and then we are storing that A value into all the different regions of the 2K of memory. So the way that this is being done is X is our offset. It's our index into our memory address. So the value of X is being added to this address. So the first time through, the value of X is 0. So added to 0 is obviously 0. Same thing with 100, 200, 400, blah, 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 right? Straightforward. Once we get through the loop once, we'll increment X and we'll do this again. And now the value of X is 1. And so we'll add 1 to all of these addresses. And what we're doing is we're clearing out all 2K of memory. But we're doing it in these chunks here because this is an 8-bit CPU, so you can't increment X to be any bigger than 255, which means that the only way you can initialize all 2K of memory is by doing it 255 bytes at a time. And what we're essentially doing is we're doing it in, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 256 byte segments at a time. This last one is different because this one is used for sprite memory. And so what we're doing is we're initializing it so the sprites all get pushed off screen so that we don't get any visual garbage on the screen if we initialize them to the top to 0, 0, they're going to show up in the top left of the screen, especially if we actually have character ROM data for sprites and stuff like that. And we don't want that. We want them all pushed off of the screen so that they can't be seen until such time that we're ready to use them. The reason this gets done in the RAM is because the NES has dynamic RAM for its sprites, which means that it has to be refreshed every cycle, every frame of drawing. Unlike the background memory, this was done because it was cheaper to use dynamic RAM for the sprites. So that was the trade-off, and so you have to use the 256 bytes of memory here in this one chunk to keep track of the hardware sprite positions and configuration. Now you can choose which chunk of memory you want depending on how your game works. In this case, we're using the values from address 300 to 3FF, but you could move it to 4004FF or whatever you want, whatever makes sense for your game. You just have to be consistent about it. So we're looping through here. We're incrementing X and doing this over and over again. You'll notice that I do branch if not equal and then jumping to clear mem if it's not equal. What that means here in this case is you'll notice we're not doing any sort of comparison, but by incrementing X over and over again, once X hits 255 and we increment it one more time, it will roll over back to 0. And the CPU 0 flag will be set to 1, which is how the CPU knows that something is, two numbers are equal. There's basically a rule that if two numbers are equal, when you compare them, the 0 flag is set, which means that branch if not equal is looking at the 0 flag. The reason this happens is because internally, comparisons like this in the 6502, and I believe this is true of most processors, is done by just doing a subtraction of the two numbers that you're comparing. So if they were equal, then obviously the subtraction would result in a 0, which is then why this is looking at the 0 flag. All right, so we've looped through this 256 times, or 256 times, clear out the memory. Now what we're going to do is we're going to load this flag variable with this value here. Now the reason we're doing that is because we need to set it with a value that we can use to control the PPU. So I'm just checking which register we are storing it into. So that flag register, that flag variable is being stored later on in the 2002. Wait, is it 2002 or 2001? 2001 register. And you can see that we're setting 2 bits. We are setting the highest bit, which is the blue emphasis bit. And we're also setting this 4th bit here, which is show background. So we're doing this because we want to show the background to have something get drawn on the screen. And we're setting this emphasize blue because we want to heighten the blue value that's displayed by the PPU of that background that we're drawing. Now the background is essentially nothing, but it will still add blue to that nothing to give you a bluish background. And what we're going to do in our code is we're essentially going to toggle this emphasize blue bit on and off with a counter acting as a timer so that we can do it at a regular interval. So we set the flag that way because we're not going to read the register. You can't. It's a writable register only. So we're going to use this flag variable to keep track of what the value is in the register. And then we're going to wait for our second VBlank because now we're getting to the point where we actually want to update the PPU, and you're not supposed to do that until after the second VBlank. So we wait for another VBlank to occur, and then once we're feeling good about that, we're going to load A with 0. this was long form binary because I think I was doing something different there before, but it's just the value 0. We're storing that into counter. We're storing that into 2001 just to zero it out again. Then we're loading A with the same thing we have in the flag variable just to set 2000. Let's see, what are we setting in that? We're telling 2000 that we want to use sprite pattern table 1. I'm not sure that we actually needed to do that, but sure, that's fine. And then we are also telling the PPU that we want it to start generating the non-maskable interrupt to call our code at vblank here. Then we are loading 3F into A, and we are storing that into 2006, which is an address register for the PPU. You can use that to update the values of... Oh, I see. That's why we're doing this. Okay. I had forgotten why I was doing this. So we're loading 3F, which is the first part of the address 3F00 into the register at address 2006, which we're using to tell the PPU we want to write at the address 3F00 in the PPU RAM, because one thing to keep in mind, the CPU and the PPU both have their own RAM that's used for different purposes. And the address 3F00 is palette memory. So we are telling the PPU that we want to update the background color by saying, okay, the address is 3F, so we store the first part of that into 2006. Then the second part is 00, we store that into 2006. So we've told it, okay, we want to write to 3F00, and then we want to store the value. In this case, the value will be 0 into 2007. That register is the register that you actually use to update PPU memory. Now, remember, because the RAM between the PPU and the CPU are separate, the only way you can update PPU memory is through the register 2007 for things like palettes. So that is what we are doing, is we are telling the PPU, hey, go update that address now that we told you about with the value 0. And if you look at this palette, can I get a bigger view? You can see 0 is not black, it's actually like a dark gray. It's this dark gray color. So that's why we go between this dark gray and sort of like a bluish gray as we toggle the blue emphasis bit on and off. One thing to note, even though we told the PPU that we want non-maskable interrupts to occur, we should still clear the interrupt inhibiting flag, which we set over here, because we're done with anything that would be problematic if an interrupt occurred. And keep in mind that the reason it's called non-maskable is because once you turn it on, even the SEI doesn't stop it from happening. But again, sort of as a good best practice, you want to set it in the beginning to disable all interrupts and kind of do your housekeeping. Set the PPU to do its interrupts once you're ready, and then clear the interrupt inhibitor and let interrupts occur should they need to. And then we have this code here that just loops back to forever, literally forever, as long as your 6502 is powered on and you didn't hit the reset button, because all the rest of the interesting code happens here in the vblank portion of the code. So what we're doing in the vblank portion of the code is we are incrementing counter. And the reason we're incrementing the counter is because we are using it as I said before, our timer. I believe, let's see. Yep. So what we're doing is we are incrementing it. We are then comparing it to 3C, which is 60. If it's not equal, we're just going to this label and we are returning from the interrupt. Very important that you remember to return from the interrupt. If it's equal to 60, that means we have done 60 frames drawn by the PPU, which is 1 second. And so what we want to do now is we want to turn off the emphasis bit, or turn it back on if it was off. That's why we have this flag variable, because like I said, you can't read the register back from the PPU. So the flag represents the state that we want the register to be in. So if we hit 60, which means that 1 second has passed because the NES, at least in NTSC regions, runs at 60 frames per second. In PAL, it would be 50 frames per second. So this will run a little bit off on a PAL system. But in an NTSC, it would be timed to 1 second correctly. If we hit 60 frames, then we are going to take our flag variable and load it into A, and then we're going to use exclusive OR. The way exclusive OR works, if you don't know, so a bitwise OR says that if you have a 0 and a 0, the result is 0. If you have 0 and 1, the result is 1. If you have 1 and 1, the result is 1. Right? So as long as one of the bits that you're doing the bitwise OR on is 1, you get a resulting 1. Exclusive OR is different because the only way you can get 1 is if only one of the bits is 1. So if you have a 0 and a 0, you get 0. If you have a 0 and a 1, you get 1. But if you have a 1 and a 1, you get 0. So what we're doing here is we are using this exclusive OR repeatedly against flag, because when we come in here the first time, that bit that we're checking against here is 1. So when we do the exclusive OR, the 1 and the 1 will make it 0 as the result. And so then that turns the emphasis bit off. We store that into the register. The next time we come in through here, we do the exclusive OR on the flag, and it will have been 0 on that bit. So doing the exclusive OR, you get a 1 in the result, and now you have the emphasis bit back on. So once we've loaded flag into A and we do our exclusive OR, we're satisfied with the result of that stored into flag because we need to save that. It's only in the register at this time. If you forget to store it, this will not work because it does not automatically store it into the RAM. You have to do that using store A. Then we store it back into 2001, the register and the PPU that, like I said, will control the emphasis bit. And so we will get the emphasis, blue emphasis turning on and off once every second. And then we load A with 0 and initialize counter back to 0 so that it will count back up to 60 again. And that's it. That's the whole program. Hopefully this was clear. Again, if this was confusing because you didn't watch the other episodes, you probably should. I go into a lot more detail. I explain binary notation and hexadecimal, and I go through this whole thing again with visual aids and a lot more detail, I think, than what I was able to do here. But hopefully this covers what you were looking for. Let me know in the comments below, and I'll talk to you all later. Thanks for watching, and have a great day.